who's also on the call. So as well as myself and Mattia, who'll give the lecture, we've got Grace here. Grace, do you want to briefly say hello?
Yeah, hello everyone.
So Grace is running the Easter School, which is running alongside. So some of you are part of that. I know there's additional stuff afterwards. And what we'll do is at the end of this, that Easter School stuff will move into a breakout room for continuing the next session of that. If any of you are listening to that and saying, Easter School, what Easter School? That sounds like fun. I'd like to join. And then the best thing to do is to drop Grace a message in the Teams chat, which you should be able to do. And then Grace can respond to that there. Okay. So the plan is a lecture which gives you a bit of a feel for how lectures are at Cardiff. Obviously, we are in a slightly different situation to the way we normally like to be, being in lecture theatres and in person. In any other year, well, actually not last year either at this point, but 2 years ago, we'd have, and hopefully next year can get people into Cardiff, into a lecture theatre. But at the moment, of course, that's not possible. So Mattia here is going to give a snippet of a lecture, a small bit of a lecture, about 15 minutes long or thereabouts, which will give you a feel for what lectures are like. It should be something that you can access. I won't give the game away on what it's about. I'll let Mattia explain that when he gives his lecture. And there'll be time for questions afterwards as well. Okay, so you should be able to chat. If I could ask you, all are muted. You've also got your Zoom etiquette is excellent. So if you want to ask a question at any point, then I mean you can stick your hand up, or you can leave it till the end as well. Okay, so I shall stop talking and I will hand over to Mattia. I will turn off my video while Mattia is giving the lecture, just so I don't distract anything if people are on gallery view, but I am still here listening, and we'll probably pop up again later on. So Mattia, over to you.
Okay, thank you very much. Good afternoon again, everyone. So let me first start the sharing. Okay. Oh, no, sorry. I got the wrong one. That is for later. Yeah, this is... Okay. So good afternoon, everyone. I'm Mattia Negraro. As I said before, I'm an astrophysicist. I'm also a senior lecturer here at the School of Physics and Astronomy at Cardiff University. And I teach in particular a third-year module on cosmology. Okay, and in fact, the lecture I'm going to give you is related to this field of astronomy. So in the next 10 minutes or so, I will deliver this mini lecture. And essentially, this mini lecture is to give you an idea of how I normally deliver a lecture in my module. So I'm going to use exactly the same kind of instrument I would be using in a normal lecture, which are essentially PowerPoint slides and the iPad, which I have in here to do some handwritten derivation. Okay. So this lecture is inspired by my cosmology module. So I picked up this topic, which is the expansion of the universe and the significance of the Hubble's law. So you may be already aware of the fact that the universe is expanding. You may have heard about that. And in particular, you may have heard about the name of Edwin Hubble and the Hubble's law. Edwin Hubble is, in fact, normally associated with the discovery of the expansion of the universe. But actually, that is not entirely correct, because when in 1929, Edwin Hubble published his famous Hubble's law, okay, that people normally believe to be the demonstration of the fact that the universe is expanding, people already knew that the universe was in a dynamical state, okay? And so the Hubble's law has actually a deeper significance, a deeper meaning, which is what I will try to explain in this mini lecture, okay? Oops. So the universe is made up by a lot of stuff, but the visible building blocks of the universe are what we refer to as galaxies. And here you can see a sample of nice images of galaxies produced by the Hubble Space Telescope. So these galaxies are systems made up of hundreds of billions of stars, okay? And the Milky Way, the galaxy we live in, is just one example. In fact, it is estimated that in the observable universe, there are more than 1,000 of billions of these systems. And as you can see in this pretty picture, they come in different forms and shape. But essentially, we use this luminous object to trace the dynamical state of the universe. And as I mentioned before, before the 1929, people already knew that these galaxies were moving, they were not static in space. And in particular, they were moving away from us, okay? So no matter in which direction in the sky you look at, you will see these galaxies moving away from us. And that definitely implies that the universe is in some sort of expansion. So how do we model this expansion? Well, the simple case of an expansion you can think of is the one associated with an explosion. So if you have an explosion, you have a center of explosion from which all the debris move away. Okay, so if we wanted to interpret the observation that galaxies are moving away from us, so the universe is expanding, by using this model, we have to conclude that there was an explosion of some sort in the past, but we happen to live exactly at the center of that expansion in order to explain the fact that galaxies are moving away from us in each direction. Okay, we will not be able to explain that if we were one of the debris moving away from the center of expansion, because we will see also other debris moving toward us. Now, this kind of interpretation has an issue, because how do you explain the fact that we live exactly at the center of this expansion? Some people may simply answer that that is not an issue, it's just a coincidence, okay, that we happen to live in there. But actually, scientists do not believe in coincidences. We always need to come up with an explanation for everything, okay? And besides that, every time history teaches us that every time we believed we were at the center of something, we were wrong. We thought we were the center of the solar system, we were wrong. At some point by the 18th century, we thought we were at the center of the Milky Way, and we were wrong, okay, because we are not at the center of the Milky Way. And also still at the start of the 20th century, people believe that the Milky Way was the center of the universe. And now we know that is not the case, okay? So in physics, in science, we state that we do not occupy a special position in the universe. And that goes under the name of Copernicum Principle, okay? So if that is the case, it means that when we observe the universe, okay, and we draw some conclusion about the universe, about the property of the universe, those same conclusions should be the same we would infer if we were living in any other position in the universe. So in other words, if we see galaxies moving away from our position, okay, we should be observing exactly the same galaxies moving away from our position, even if we were living in any other galaxy in the universe. So a conclusion of this, of combining the observation that galaxies are moving away from us with the Copernican principle, the conclusion of this is that all galaxies in the universe should be moving away one from the others, okay? So in other words, you have an expansion, but happening with respect to every point. And of course, you can't explain this kind of expansion anymore by using the example of the explosion, because in that case, you have just one center of expansion. And so how do you explain, how do you model, represent an expansion that happens with respect to virtually an infinite number of centers, number of points? Well, this is the moment in which we need to abandon our standard idea of space as something that is unchanging, static, and embrace this sort of crazy idea of space brought forward by Albert Einstein via his theory of general relativity, according to which space is not static at all, but is more like an elastic fabric that can bend, can stretch, and can change with time. Okay, and so if you embrace this idea, you can actually come up with a model of the expansion of the universe. And the simplest way of visualizing it is that of thinking at the surface of an elastic balloon that is being inflating. Okay, and here you can see a cartoon of this. So imagine that the surface of this balloon is space. Of course, this is a two-dimensional representation of it, okay, but it still conveys the message, the concept. And galaxies are located in space. So imagine galaxies attached to this surface. So if you inflate this balloon, what happens is that galaxies are all moving away one from the other. And so there you have your expansion happening with respect to every galaxy. So in this model, in this idea of stretching space, the expansion of the universe is actually a consequence of the space being stretched. And by doing that, is dragging away galaxies one from the other, okay? And this leads us to the Hubble. So as I mentioned before, Hubble published his law in 1929. And essentially this law is a relation between the velocity at which galaxies are moving away from us, here represented in the y-axis, and the distance at which these galaxies are represented in the x-axis. This is, by the way, the original plot published by Hubble in 1929. So there is a lot of scatter nowadays. Of course, we have better plots, but I thought it was nicer to show you the original plot, okay, that is now nearly 100 years old. So Hubble measured this velocity, measured the distance, and then when he plotted those two quantities in this graph, he found that they were proportional one to the other, okay? So this relation of proportionality is what goes under the name of Hubble's law, and the constant of proportionality is the famous Hubble constant, okay? So this relation, okay, is extremely important because it's not the demonstration that the universe is expanding. As I said before, people already knew about the expansion of the universe before 1920 now. But it is actually the demonstration that the universe is expanding exactly as predicted by the theory of general relativity. So as a consequence of the stretching of space itself. So if the universe is expanding as a consequence of the stretching of space, you expect to see a relation of proportionality between the velocity at which galaxies are moving away one from the other and their distance. Okay, so this is the real meaning of the Hubble's law. Okay, and I'm going to conclude this mini lecture, but actually doing a simple derivation to convince you about this, that if you have a space that is stretching, okay, you end up with a linear relation between the velocity and the distance. And so I'm switching now to the iPad. Okay, as I said, that is another standard tool that I use for my lecture to do handwritten derivations. So it should appear, there it is, okay. And I'm going to do this simple derivation. So I'm going to draw a circle in here. Okay. And the nice thing of using the iPad is that I can draw these perfect circles. And imagine that this circle is the inflating balloon I showed you before. In this case, it's even simpler because it's actually a one-dimensional surface. Okay. And I'm going to indicate with capital R the radius of this circle. Okay. And then I'm going to identify two galaxies, call it Galaxy A and Galaxy B, on this surface. Okay, so the surface, the universe in this case is represented by the surface of this circle. Okay, and let me indicate with theta the angle subtended by the distance between the two galaxies. Let me indicate it in red. So this is the distance between the two galaxies, of course, along this space, and I indicate it with capital D. Okay. So this circle is expanding, okay? And I make an assumption in here. I assume that it is expanding at the same rate everywhere, which means that it doesn't get deformed during the expansion, so it keeps the same shape, okay? And that means that after a certain amount of time, this circle would look something like this. I'm not going to draw it all, okay? And therefore, this galaxy after a certain amount of time, have moved into this position. And therefore, their distance, as you can see, has increased, okay? Because this is expanding, r will be a function of time, so I can indicate it as r of t, and also the distance is a function of time. However, because of the hypothesis I've made that this circle is expanding without getting deformed, so the expansion rate is the same in every point, a consequence of this is that the theta is a constant. So it doesn't change with time, okay? By the way, notice that I can write the distance at any moment in time as the radius times theta, if theta is expressed in radians, okay? So now I have set up and specify all the things I need to do now the demonstration. So what I want to do is to compute the velocity at which those two galaxies are moving away one from the other. And the velocity, by definition, is the derivative with respect to time of the function you are considering, so in this case, the distance. Okay, now, I don't know if you have come across the concept of derivative, but essentially, if you haven't, don't worry, you will see it in the first year at the uni, in the maths module. But essentially, the derivative measures the variation with respect, in this case, to time, of the given function, in this case, the distance. So the function is changed with respect to another variable, okay? And this is often indicated also with a simple dot on top of the function that you are, for which you are taking the derivative, okay? So if I compute this, essentially I just need to replace in here the expression for the distance. So I have r of t times theta, and I'm computing the derivative of all the stuff that is inside the parentheses. And now I can use a property of the derivative, which says that if you take the derivative of a function times a constant, the derivative is simply the constant times the derivative of the function. So in other words, you can take any constant outside the derivation. And so I can rewrite this as theta times the derivative of r, because only r depends on time, okay? And we are getting there, because what I'm going to do now is to use a simple trick. So I'm going to multiply and divide my expression by capital R. You see, I've multiplied and divided by capital R. Why I did that? Because this guy here is just the distance, okay? And let me indicate this guy here, which is a function of time, as a capital HT, okay? And so here I have my final expression. I have that the velocity is equal to capital HT times dt, okay? And for a given fixed moment in time, this quantity is the same for each pair of points I consider. And so there you have, for each moment in time, a linear relation, a relation of proportionality between the velocity and the distance. And if you compute this at the present time, so t equal to t naught, if t naught represents the present time, you have the value of this h of t function calculated at the present time together with all the other quantity. And this is what we normally indicate with h naught, the Hubble constant. So the Hubble constant is just the value at the present time of this more general function, h of t, that we call in cosmology the Hubble parameter. And so this is a very simple demonstration. Of course, in the cosmology module, I do it in a more rigorous way, using all the concept of metric, of an expanding universe that comes from general relativity. But this, even if it's a simple calculation, I still do this in my cosmology module to easily convince my students that you have indeed the relation of proportionality between the velocity at which galaxies are moving away and their distance as a consequence of the stretching of space. And so I wanted to stress again this concept that the Hubble's law is not the demonstration that the universe is expanding. It's actually the demonstration that the universe is expanding as a consequence of the stretching of space. Okay? And so this concludes this mini lecture where I showed you the kind of tool I use to deliver the lecture. So if you have any question, you're more than welcome to ask them, and I'm more than happy to answer. You can type them in the chat, I mean, if you don't want to.
Thank you very much, Mattia. Yeah, so as Mattia said, yes, if you want to ask questions in the chat, then please feel free to type away. If you'd like to ask them verbally, then generally, I don't know how exactly Mattia does it in lectures, but commonly use the raise hand button is a nice way of doing it. Or there's not too many people here to all overlap with each other, I imagine.
Yeah, can answer I see one question in the chat. Yes, definitely. We used to record the lecture even in the pre-COVID era. Okay, and essentially after the lecture had been recorded, we put them in Learning Center, which is the platform where the students can access all the learning material. And so they are almost immediately by the same day available to the students. And of course, we are doing much more so now with COVID. We record everything. I mean, we do live online session, but they are all being recorded.
It's worth also adding that meant we as staff here felt we were fairly well prepared for doing this. Although, of course, all our teaching has gone online rather than in person for the last year now, because we had the infrastructure there to record lectures, and students were used to going and finding the lectures online and using the online platforms to submit work, to access work, to get their assignments and so on. There was relatively little change in that side of things. That being said, we are looking forward to getting back into lecture theatres. I'm sure Mattia would agree. And it's not just for learning difficulty students, it's for anyone who can access them, anyone who misses a lecture at all, then those are there as well. Okay, we have a cosmology related question, which I'll let Mattia take as well.
Yes, so when the universe expands on redshift light, it increases its wavelength and therefore decreases the energy of the photon. Where does this energy go? Okay, so this is a kind of question I get quite often. And although is quite an obvious question to ask, the answer is not that straightforward, in the sense that to give a proper answer to this question, you would really need to consider several effects that happens in general relativity. But the easy answer is that kind of energy goes into the expansion of the universe itself. Somehow. I know that this is not the most satisfying kind of question, but as I said, to answer this properly, you definitely need to have some tools from general relativity. And there are many different things in general relativity that happens that are not that straightforward to explain in a straightforward way, let's say. So, sorry, I can't be more specific.
This comes from the idea that the conservation of energy being a sort of one of the prime tenets of physics, of course. But I guess the key thing there, Mattia, is that it's conservation of energy in a closed system.
Exactly.
That's what's not here. That's what doesn't take place here.
Usually what you do is you consider energy densities rather than the absolute values of energies at least in cosmology. So recession velocity affected significantly by gravity. So we have another question. Is the recession velocity affected significantly by gravity? I mean, in general relativity, okay, let's put it this way. In general relativity, gravity is an expression of the distortion of space. So in general relativity, you don't need the concept of force anymore, okay? Because what happens is that what we would normally refer to as a force is actually a consequence of space being not flat anymore, but have some sort of curvature, okay? And so if, imagine, let's keep it local for the moment. Let's consider the solar system, okay? Just to make clear this idea of forces being replaced by the distortion of space, okay? We would normally think about a planet orbiting around the sun because it's constantly pulled by this invisible force. In general relativity, that is not the case anymore. The idea is that the sun is distorting space locally, okay? So you can imagine again this elastic fabric being deformed by the sun. And the Earth, which is much lighter, is like a ping pong ball moving on this distorted surface, and therefore being trapped in this deep well produced by the sun. And there you have essentially the net effect is that of a lighter ball circling around this potential well, okay, that is created by this much heavier ball that is the sun, okay? And so if you have, in the case of galaxies located in a region that contains a lot of matter, for example, a galaxy cluster or a supercluster, okay, the local effect of gravity has an impact, okay, on the photons, okay, that are being released by this galaxy, because the photons themselves, they find themselves trapped into this distorted space. And so they will lose energy in trying to escape from this potential well in which they are trapped. And that would create an extra sort of redshift in the light. But the effect that you have with respect to the overall expansion of the universe is much, much smaller. So I hope that answered your question, Ben. So there is an effect by gravity, but is not as significant as the one due to the overall expansion, stretching of space.
I think there's an aspect there as well where if you think about the four fundamental forces or interactions that we think of in the universe, so you may have heard at school about the strong nuclear force and the weak nuclear force and the electromagnetic interaction, and then of course gravity as well. They kind of go in that order as how strong they are, although they have different ranges. So the electromagnetic force is stronger than gravity. So I can lift, my phone. It's blending into the background. I can lift my phone up and counteract the effect of 6 times 10 to the 24 kilograms, a few thousand kilometers down there. And I guess, Mattia, is it fair to say that the expansion of the on local scales, that gravity is then stronger, of course, than the expansion of the effect of the expansion of the universe? So on a local scale, we don't find the Earth stretching. We've not got a million times bigger over the past billion years, or the planet hasn't, because gravity is much stronger than that kind of Hubble effect, if you like.
Yeah. In fact, in cosmology, you just focus on the largest scales, okay? And so you consider what we call the Hubble's flow, so the overall stretching of space. But of course, when you go local, okay, you start to have all inhomogeneity in the distribution of matter that create this extra deformation in the fabric of space. And so locally, this effect becomes more important in the overall expansion of the universe. So it takes over. And that means that in some cases, you don't even observe a redshift anymore. If you have already come across this concept of redshift, so light becoming redder and redder because of the expansion of the universe, but actually it appears bluer. So you have a blue shift rather than the redshift. For example, the Andromeda Galaxy is so close to us that is locally detached from the Hubble flow, and it is moving toward us, or you can see from the Andromeda point of view, we are moving towards the Andromeda Galaxy. And so one with respect to the other, we have a positive redshift, or in other words, a blue shift, okay, because locally we live in this, together with the Andromeda Galaxy and many other galaxies, we live in this region that contains all this inhomogeneity in the distribution of matter, and that has a much important effect compared to the overall expansion of the universe, the Hubble's flow. But still, the effect of gravity on redshift is still very small, though, in terms of the photon losing energy, okay?
Sure, yes. Okay, thank you for that. So, are there any more questions from anyone who was watching that lecture? Anyone got any more questions? Type them into the chat, or raise your hand, or unmute, or something, and we can try and answer those just before we finish the lecture side of this. Okay, so the plan now, I'll just talk just in case anyone is frantically typing. The plan now is that we move into the Easter School session, and so Grace, I think, am I right in thinking there's just a breakout room for the Easter School participants?
Yeah, I've added everyone who I think is on the Easter School, but obviously some people have names who are slightly cryptic. So what I'll do is I can open that room now and take those students there. If there's anyone who's not automatically taken into the room, if they let Chris know, then Chris can.
I should be able to
okay?
sign people. Yeah, and then everyone else is welcome here, and Mattia may be able to answer a couple of other questions if people still have them. Okay.
Cool. I'll open that and go there now, and then if anyone's left, let Chris know.
Okay. So for those, you'll probably see a box that pops up and says you've been asked to join a breakout room. So if you click accept on that box, if you've not already, and there we go. And I think that is almost everyone. There we go. So is there anyone here who thinks they're part of the Easter School and therefore should be in that Easter School session? Or, as I said earlier, is sitting here thinking they really want to be part of that Easter School that we're running this week and next week? Okay. All right. Well, there are 3 people left, so I don't know whether any of you here have any more questions for Mattia that you want to ask. Now is your chance to ask those questions in this last little bit before we finish. I may disappear and I have to head off and talk to the Easter School students in a second, but feel free to ask any questions now if you have any. Okay. All right. In that case, I think this part of it is over. So thank you very much to the 3 of you for coming along. I hope that's been interesting. That's been useful. Thank you for the questions that were asked by everyone. And if you want to know about more events, then don't forget to go back onto the booking link. There's a medical physics and a physics lecture next week. We're actually in the course of we've had to do a little bit of a change. So I think it's now medical physics on the Monday and physics on the Tuesday. I'll be emailing those booked onto those in due course. But if you could, if you're interested in attending them, and there's a chance to chat to staff and students one-on-one coming up on Thursday as well. So do go onto that booking link that you got emailed and have a look there. Okay, but for this part, then I think we're done. Mattia, you're more than welcome to come over to the Easter School and see what's going on if you want, to see if there's any more questions. But thank you very much to those who've come along.